Hi everyone. So in this video, we're going to be talking about arc length, which is basically an application of integration. So what we'll see is that there's a formula that involves taking an integral that allows us to find, typically when we're talking about integrals, we've been finding areas, right? Like the area bounded by a function. But what we'll see is that we can also use an integral to find the length of a portion of a graph. So for example, let's say that this is a function f of x, and let's say we want to know how long it is between two particular x values a and b. So in other words, we're trying to figure out, what is the length of this piece that I'm going to highlight here. So it's not a straight line, right? It's a curved shape, and that's really why that word arc is in there. And so you can't just use like the distance formula, for example, because the distance formula would give you a straight line distance, right? It would give you like this distance, and we want the actual distance of the graph. And so it turns out that there's a formula for it, which is that the length of the arc of this function, f of x, from x is equal to a to x is equal to b is the following. So you're going to take the integral from a to b, but you're not going to take the integral of the function. What you're going to do is you're going to take the integral of the square root of 1 plus the derivative of the function. So let me actually write it this way, f prime of x squared. And sometimes this is also written as, I'll just write it both ways, I mean, they're equivalent. But some people will also write it as 1 plus dy dx squared. It's just something about that looks a little bit nicer, I think. And then there's also a version of this that works for functions of y. So, we can use this not only when you have something like what we have here, so this is a function of x, but later on, we'll do an example of a sideways parabola, which is not a function of x, it's a function of y. And so you can use the formula the exact same way. So let me just write that down. So the length of the arc of a function of y from y is equal to a to y is equal to b, that's going to be basically the same thing. The integral from a to b of the square root of 1 plus the derivative, which now will be f prime of y squared dy. And then another way of writing that would be the integral from a to b of the square root of 1 plus dx dy, which probably seems a little weird, but think about, what does dy dx mean? It basically means the rate of change of y with respect to x. And so that's what you use when y is a function of x. If x is a function of y, well then you take the rate of change of x with respect to y. So it's really just the idea that x and y are kind of reversing here. So the majority of this video, we're going to do some examples of this, but I want to show you first the proof of this formula, and we'll prove the form that is for functions of x, because functions of y, it's basically the exact same idea. So if you are just like absolutely not interested in seeing where this formula comes from, you can skip this. I know that this is probably, it's the end of the quarter, there's a lot of stuff stacking up, but I think the proof is kind of interesting and rather intuitive. I don't prove like everything in this class. I try to focus on only proving the things that actually give you a little bit of insight. And so I think this one has a little bit of insight to it. So I think it's worth listening to, following along. Okay, so how are we going to prove this formula? Well, think about how I kind of explained where the the disc and washer method came from, or the cylinder method, right? It was this idea of taking whatever shape it was that we were working with and kind of breaking it down into pieces, and then figuring out, how would you find whatever information you need about this piece, and then you add them all up, and that's how it becomes an integral. So basically what I'm saying here is that, so let's say that we wanted to approximate the length. Again, I'll just put in some, bounds here. So we can approximate the length of the arc of f of x from A to B. So how could we approximate this and without using calculus? Well, if we break this interval from A to B into some pieces, so I'm just going to kind of go through and let me actually, for the sake of being able to, for the sake of being able to actually draw something that makes sense, I'm not going to use a lot of pieces, but obviously if you wanted to get a really good approximation, as we've seen in other things, you would want to use a lot of pieces. So let's say we break this into a few different pieces, and this is going to be x1, x2, x3, x4, x5. So what we could do is we could go to our curve and kind of break it into, like, go to each of these points. So here's x1 and x2, and then x3, x4, and x5. So what we could do is, instead of finding the curved distance between these 2 points, we could find the straight line distance, right? So if you went through and you took these straight line distances between each of these points, it wouldn't give you the exact length because it wouldn't be able to capture all of the sort of curves of it, but it would at least give you an approximation, the same way that rectangles can give you an approximation of area. It's a very, very similar idea here. So we can approximate the length of the arc from A to B by breaking A, B into pieces and finding what I'll call, again, straight line distances. For each piece. So why is that, why can we use straight line distance? Well, because for that you can just do the distance formula, right? So the whole reason we need this new formula is because this graph is curved. So if we can break it into pieces that are straight lines, that will then enable us to use the distance formula. So let's focus on just kind of one little portion of this graph. So I'm gonna focus in on this portion right here. So I'm gonna use another color here, and I'm just gonna draw like a little right triangle. So this is gonna be the part that's kind of between x2 and x3. But let's maybe just call this the ith segment, because I wanna be as general as possible here. So if we wanted to find the length of the ith segment, so let's call that L sub I. So how would we find that? Well, let's call the distance from x2 to x3, or from x1 to x2, whatever, any of these distances, let's call that delta x, as we tend to do in these problems. So this distance here we're going to call delta x, and let me maybe use a couple different colors. So we'll call this delta x. And then how would you find the vertical distance here? Well, if you think about it, this the y-coordinate of this lower point, right, would be f of x2. And then the height of the higher point would be f of x3. And so that means that the vertical side of this triangle would be f of x3 minus f of x2, right? And so how would we find the part that we're actually looking for, right? We're looking for the distance between, the straight line distance between these two kind of highlighted points. Well, we could just apply the Pythagorean theorem, which is basically the same thing as the distance formula. So that would be, Li would be approximately equal to the square root of delta x squared plus, and I'm just going to call this actually, instead of calling it, and let me actually go in with this color so that we can keep track of where everything came from. So delta x squared, and I'll put parentheses as well. And then rather than write this for x3 and x2, I'm going to just kind of be more general, because here we're talking about the ith segment. So I'm going to say f of xi plus 1 minus f of xi. So it's basically just saying, you have some segment you're looking at, like, for example, x3 and x2 or x4 and x3. It doesn't really matter. You're just looking at some sort of adjacent y values. Okay, so does this make sense so far? So this is just coming from basically the Pythagorean theorem. Okay, so now we're going to do kind of another simplification here, which is that let's think about how derivatives kind of come into play, right? We know, because I already gave you the formula, that there's a derivative in it. So how do derivatives come into play? Well, let's say that you found f prime of xi. So in this picture, maybe that would be f prime of x2 or x3. It doesn't really matter, but just kind of pick one x value. And let's say you found f prime of that. Well, that would be pretty similar to the slope of the line that we drew, right? It's not going to be exactly the same, but especially if we're dividing this into like many intervals, right? I divided it into 4 because I wanted everything to be big enough that we could actually see it. But if you're trying to get a good approximation, you would divide this into like many little pieces. And so what I'm saying here is that if you take the derivative at a particular x value, so let's say that you're taking the derivative at x2, that would be the slope of the tangent line at x2, right? That's what f prime of x2 would represent. So f prime of xi is going to be not exactly equal to, but at least approximately equal to the slope of the hypotenuse of this right triangle, right? And in this picture, you can tell they're not that close, but again, the smaller these intervals are, the closer that result will actually be. So how would you find the slope of this hypotenuse? And maybe I'll even just write that down. The slope of the hypotenuse. So how would you find the slope of that hypotenuse? Well, you would do change in y over change in x, right? So that would be f of xi plus 1 minus f of xi divided by delta x. Right? Because it's just change in y over change in x. And literally, if you look at this triangle here, change in y is the subtraction of the x or the y coordinates, and delta x is the change in x. So this right here would be the slope of the hypotenuse. And so what that means is that we can replace, or actually, let me do one more step before the next thing I was going to say. So right now we're saying that the derivative of xi is approximately equal to this slope here. So let's multiply both sides by a delta x. So that's going to give us f of xi, or f prime of xi, times delta x is approximately equal to those vertical changes, right? F of xi plus 1 minus f of xi. So what that means is that we can now go into our expression here for the length of the ith segment, and we're going to replace where it has this, right? We have a place where this is within our statement. We're going to replace it instead with this. So we're going to put f prime of xi times delta x in instead of where we have this orange thing. So we now are saying that the length of this ith segment is approximately equal to delta x squared plus, and then let's put in our next thing. So f prime of xi times delta x all squared. And so now let's pull out actually from both of these. So I'm going to do kind of an algebra trick here. So we can factor out a delta x from both of these two things, right? Or a delta x squared. So we can rewrite this as the square root of delta x squared times 1 plus f prime of xi. And then, so the 1 we don't have to square, but actually, sorry, I did something wrong here. I should put extra parentheses around this, like that, right? So I just factored out a delta x squared. And so the reason I did that is because now we can actually pull it outside of the square root, right? Because we have a square root of delta x squared. And we're assuming that delta x is positive because it's a distance, so we can just take it outside of this whole thing. So I'm actually going to put it at the end. So we're going to rewrite this as 1 plus f prime of xi squared and then now the delta x is on the outside and it doesn't have a square on it. Okay, so we're now done writing down in kind of the most simple form possible our approximation for one of these little segments. So how would we find the overall length of this arc? We would add them all up, right? So the total length, so the total length from A to B is going to be, so let's call it L, is approximately equal to the sum from 1 to n of all of these segments, right? So adding up all of the different line segments. And another way of writing that would be what we had above, right? We had the sum from 1 to n, so now we can replace Li with this expression we just came up with, which is the square root of 1 plus f prime of xi squared times delta x. And so how do we find the exact length? Well, this is something we've seen a good number of times right now. We can take the limit, right? So L is going to be exactly equal to the limit as n approaches infinity of the sum from 1 to n of the square root of 1 plus the derivative at this ith point squared times delta x. And so we've seen that when you take the limit of a sum, it becomes an integral. So this is going to become the integral, and specifically an integral from a to b of, so the square root is still here, and the f of xi just becomes, or f prime of xi just becomes f prime of x. And so we're taking f prime of x and squaring it, and then the delta x becomes a dx. So that's our formula. So really, at the end of the day, I know there's a lot of details in this proof, but really what it comes down to is that the integral basically comes from the distance formula, or the Pythagorean theorem, in combination with the fact that the derivative kind of is also related to the hypotenuse of that triangle, right? The length and the derivative have this kind of relationship when you look at the distance formula or a right triangle. There's, that relationship is what gives us this formula. Okay, so let's jump into some examples. So the first example I want to look at is we're going to find the length of the arc. So this is y is equal to x to the 3 halves. So find the length of the arc of y is equal to x to the 3 halves from x is equal to, where we go, 1 to x is equal to 4. So I just want to highlight what that length is in this picture, because I think it's kind of nice. You can actually usually see whether your answer is reasonable just by kind of looking at the picture. So from 1 to 4 would be this portion here. Okay, so what's our formula? Well, it says that the length is going to be the integral from a to b. So the a and the b are just your x values. So we have from 1 to 4 of the square root of 1 plus, and now we need to take the derivative of our function. So in this case, because it was given to us not in f of x notation, but in y is equal to notation, I'll write it this way. So what is dy dx in this case? Well, we use the power rule, right? So we bring down that 3/2. So we have 3/2 times x to the, and we subtract 1 and we get 1/2. And so this is now going to be the integral from 1 to 4 of the square root of 1 plus, so we're going to take this derivative and square it. And let me actually, I want to add some color in here because I feel like it will help things stand out a little bit. So maybe I'll use purple for this. Okay, so we're going to take our derivative, which was 3/2 x to the 1/2, and we're going to square it. And I don't know why I wrote dy here. Sorry, that should be dx. My bad. So what happens when we square this? Well, it becomes just x, right? Like the x to the 1/2, that's square root of x. When we square it, it becomes x, and then the 3/2 becomes 9/4. So now we have the square root of 1 plus 9/4 times x dx. So how do we evaluate this? Well, this is actually just a substitution, right? Because so anytime you have something that is like a square root or 1 over or whatever it is, and you're doing it not just to x, but to basically like a linear function of x, you can always do a substitution because the derivative of that inside of the square root is just going to be a constant. So if we, or sorry, yeah, a constant times times dx. So if we let u equal 1 plus 9 over 4 times x, then du is just going to be 9 over 4 times dx. And so that means that du times 4 over 9 is going to be equal to dx. So when we do that substitution, we'll get, oh, and then we have to change the bounds, right? And so the bounds are going to become, so the lower bound is going to be, so I'll write this out here. So the lower bound is going to be 1 plus 4/9 or 9/4 times 1. So that's going to be 13 over 4. And then the upper bound is going to be 1 plus, so if you multiply 9/4 with 4, you just get 9, right? So the upper bound is 10. And so our integral is going to become the integral from 13 over 4 to 10 of square root of u du. And so the antiderivative of square root of u is going to be, so we have u to the 1/2, so we add 1 and we get u to the 3/2. And then we take the reciprocal, and that's 2/3, and we're evaluating this at 10 and at 13 over 4. And I'll save you all the kind of computation of writing that out. You can do that in your calculator, and basically you'll get approximately 7.634. So by the way, if you were to use the distance formula to find the straight line distance between here and here, so that would just be like, that's not a straight line. That would be like this distance. That is 7.616. So it's actually really close. This was 634. What I said was that when you do a straight line, it's 616. So it's, you can tell this graph is like almost like a straight line, right? It doesn't have a lot of curvature to it. Okay, so next example I want to do is actually one where you could just use the distance formula, but I just want to show you that it still works. So in this one, I want to find the distance or the arc length, and we can still call it an arc even though it's a straight line. So find the length of the arc of y is equal to 3x minus 2 from x is equal to 2 to x is equal to 4. So that's going to be this portion here. So we have x is equal to 2 to x is equal to 4. And that's that. So we're going to be doing the integral from 2 to 4 of the square root of 1 plus, and so we want to take dy dx and square it, dx. So in this case, we just have a line, right? So the derivative of a linear function is just its slope, so it's just 3. So this is going to be a pretty friendly integral to do. We're going to get the integral from 2 to 4 of the square root of 1 plus 3 squared. And so that's going to be the integral from 2 to 4 of the square root of 10. So how do you deal with that? How do you take the antiderivative of square root of 10? Well, it's just a constant, right? So the antiderivative is just going to be the square root of 10 times x. And then we evaluate at 4 and at 2, and we get 4 times the square root of 10 minus 2 times the square root of 10, and so that just comes out to be 2 root 10. And so we can check that this works by trying the distance formula. Let's just do that real quick. So because it's a line, you don't really have to use arc length, but I think it's kind of neat to see that it actually works to do it either way. So the 2 points, right, would be 2, 4, and 4, 10. So we have 2, 4, and 4, 10. And so how does the distance formula work? Well, you take the square root of, and you subtract your 2 x coordinates, so 4 minus 2 squared, and then you subtract your 2 y coordinates, so 10 minus 4 squared. So this would be the square root of, so that's 2 squared, so that's 4. And then this is 6 squared, which is 36. And so we get square root of 40, which can also be written as square root of 4 times square root of 10 or 2 root 10. And that's exactly the same as what we got. So that's good. I'm glad they agreed. Okay, we're just going to do one more example, but this one's a little bit more involved. Basically, there's really not that many examples that we're going to be able to do just because of how the arc length formula is. If you just pick kind of a random function from this, that we've seen in this class, chances are you'll end up with an integral that is either very difficult or maybe even impossible to integrate. So you'll see there's just not that many different variations of what we already did that we can do. This is kind of the last one, which is we'll see that we have to actually use trig substitution in this integral. So for this one, we're going to find the length of the arc of, so this one now, as we said, is a function of y. So it's x is equal to y squared from y is equal to 0 to y is equal to 1. So you could do this actually, if you wanted to, you could rewrite this as a function of x and do a square root, but let's stick with it in its form and do this integrate with respect to y. So this is what we're looking for, right? This piece right here. And so we're going to do the integral from 0 to 1. So remember, we're looking at y values here. And then we're going to want to do the square root of 1 plus, and now we're going to take the derivative of x with respect to y. And integrate with respect to y. So what is dx dy? Well, again, it's, don't be thrown off by the fact that that looks a little different. It's just, you're just switching the roles of x and y. So the derivative of x is equal to 2y, or I just said it, the derivative of x is equal to y squared would be 2y. So we're going to end up with the integral from 0 to 1 of the square root of 1 plus 2y squared dy. So that simplifies to the integral from 0 to 1 of the square root of 1 plus 4y squared dy. Okay, so this at first might seem a little bit different from what we've dealt with trig substitution in the past, right? Usually our trig substitutions would be things that looked more like this, right? Square root of 4 plus y squared, right? That one we would know how to do. We would let y equal to 2 times tangent of theta. And this is a little different, right? The 4 is on the y squared, but that's okay. We actually have done examples that are kind of like this. So what we can do is factor a 4 out from both of the terms under the square root so that then it will be in the appropriate form that we want. So we can rewrite this as the integral from 0 to 1 of the square root of, so if we factor out a 4 from both, we'll have 1/4, right? That's the, if you factor out 4 from 1, you get 1/4 plus y squared. And so then we can take this 4 and actually pull it outside of the square root and then just pull it outside of the whole integral. So we now have 2 times the integral from 0 to 1 of the square root of 1/4 plus y squared. And so now we're actually, even though it's a slightly difficult one to do, we're actually in the same kind of form that we're familiar with. So we've seen that if you have an expression of the form a squared plus, I guess I'll say y squared this time because that's the variable we have, then we'll let y equal to a times tangent of theta. And so what is a in this scenario? Well, 1/4 is something squared, right? It's 1/2 squared. So in this case, we're going to let y equal 1/2 tangent of theta. And so what is dy going to be? dy is going to be 1/2 times secant squared of theta. And let's see, so we could change our bounds. Let's see if it makes sense in this case. So I think in this case, it's probably going to be preferable to kind of drop the bounds and then bring them back in at the end with the original variable. Basically, if you can easily figure out, looking at this, set like 1 is equal to 1/2 tangent of theta, and from there, if you can easily tell what theta is, then great. But in this case, I don't think the numbers work out so nicely. So let's just drop the bounds, and then at the very end, we'll bring back those bounds. So now we're going to be focusing on 2 times the integral. Again, we're going to leave it as an indefinite integral. And now we have the square root of 1/4 plus 1/2 tangent of theta squared. And then our dy is going to be replaced with 1/2 secant squared of theta. And I left off, I always do this, I forgot the d theta. Okay, so this is going to be 2 times the integral of the square root of 1/4 plus 1/4 tangent squared of theta times 1/2. Maybe let's bring that 1/2 outside and just, that will give us a coefficient of 1, so we can just get rid of it. And then we have secant squared of theta d theta. Okay, so now we can pull out a 1/4 from both of the terms in the square root, and then that will come out of the square root as a 1/2. So we'll be left with 1/2 times the integral of the square root of 1 plus tangent squared of theta times secant squared of theta. And so now we can use the identity that says that the square root of 1 plus tangent squared of theta is equal to secant of theta. So we'll have 1/2 times the integral of secant theta times secant squared of theta, and I don't know why I dropped the d theta. And so that's 1/2 times the integral of secant cubed of theta d theta. So this is actually kind of a tricky integral. We did it, I believe, in maybe the second trig integration video from maybe like a couple weeks ago. But yeah, so this one we can now kind of just, I'll probably put this on your integral table for like your next test. So I'll just write down integral table, and I'll say we did it an earlier video. It was kind of a tricky example where we had to use integration by parts and we had to like solve for the integral. Okay, so this comes out to be, so we have 1/2, and then the antiderivative of secant cubed, that has another 1/2. And then we have secant of theta times tangent of theta plus ln of absolute value of secant of theta plus tangent of theta. Okay, cool. So we already, now we have our antiderivative, but in order to use our original bounds, we have to return this to our original variable. So let's do the whole process of drawing a triangle. So let's remind ourselves what our substitution was. Our original substitution was y is equal to 1/2 tangent of theta. So let's write that down here. So we have y is equal to 1/2 times tangent of theta. And so that means that 2 times y is equal to tangent of theta. Or we could write it also as 2y over 1, right? And so that means that in our triangle, so what is tangent? Tangent is opposite over adjacent, right? So when we go and draw our triangle, we want to put our opposite side as 2y and our adjacent side as 1. And so that means if you use the Pythagorean theorem, you should get that the hypotenuse is going to be, so the square root of 1 plus 4y squared. Okay, so now we just need to figure out, we already know that tangent is equal to 2y. So we have some tangents in there that we'll be able to get rid of. Now we just need secant. So what is secant of theta? That's the one that we really need here. Is, so secant is equal to the reciprocal of cosine. So it's going to be, instead of being adjacent over hypotenuse, it's hypotenuse over adjacent. And so in this case, it's just the square root of 1 plus 4y squared. Okay, so now we can go back into our expression here. So we have 1/4 times, so for secant, we have the square root of 1 plus 4y squared. And then for tangent, that was equal to 2y. So I'll just replace tangent with 2y. And then we have ln of absolute value of, so secant again was the square root of 1 plus 4y squared. And then again, we have tangent, which was 2y. And so now we're taking this whole thing and we're evaluating it at 1 and at 0. So luckily the bounds are pretty nice, because otherwise this would be a complicated expression. So if we plug in 1, we get square root of 5 times 2 plus ln of absolute value of square root of 5 plus 2. And then if we plug in 0, let's see. We're gonna, well, we should write it out because of the ln, but we're gonna get 0. So if we plug in 0, we get, so the first part is gonna be 0, right? This part is gonna turn to 0 when you plug in 0. And then the second part will be ln of absolute value of square root of 1 plus 0. And so this is gonna be, this part altogether is gonna be ln of 1, and ln of 1 is equal to 0. So that part goes away. And so we're left with 1, and sorry, this was supposed to be 1/4. So we're left with 1/4 of 2 times the square root of 5 plus, and then we can get rid of the absolute values because square root of 5 and 2 are both positive. And this is approximately equal to 1.479. So this one was definitely a lot of work, but it's basically a good, I think, refresher on trig substitution, with the one sort of extra detail that we have seen a little bit of, where you have to factor something out in order to get the variable just to be y squared, and then you can do your trig substitution from there. All right, so that's it for this video, and yeah, I will see you in the next one.